The Ali'i o Kealani is the culmination of work done by members of three subsystems: the UAS, UGV, and image processing. These three subsystems were designated based on a bottom-up method to accomplish the mission tasks. Each subsystem created their own tasks dependent on the mission and their functional requirements. After successful testing within each subsystem, modules were integrated slowly and tested and retested to ensure success at the competition. Originally, the team had been split up based on the previous year's work as electronics, aircraft, and image processing. However, with the addition of the UGV and the complexity of issues surrounding a successful air delivery, such as recovery system and eventual parachute disengagement system, UHDT determined it would be better to resplit the subsystem based on modules that could be finished together in parallel. This has proved very successful for this past semester, and testing has gone a lot smoother. Our competition flight sequence will be as follows: takeoff, waypoint navigation, air delivery, search area tasks, then landing, all of which will be fully autonomous. We are 100% confident that the Ali'i o Kealani will achieve autonomous takeoff, flight, and landing, including waypoint capture and accuracy. For the air delivery task, we are 80% confident in accuracy within 75 feet of the target, and 90% confident that the UGV will autonomously drive to the final destination. During this time, the UAV will continue the flight sequence and search for the targets. UHDT anticipates scoring the following for object detection, classification, and localization: 60% for characterization, 50% for geolocation, 100% for actionable, and 100% for autonomy. Concluding the mission will be autonomous landing at flight line, to which UHDT is 100% confident in achieving. In order to maximize success at the competition, UHDT carried out individual component tests at each level before integrating and retesting. This bottom-up approach encourages the experimental nature of our testing and avoids problems with determining malfunctions in any individual components. An example of this testing is the autonomous payload drop after testing the autonomous takeoff and flight to ensure that any possible problems that might arise were isolated specifically to the payload drop module, and this process was done with each component. The team began working with modules done from previous years, such as autonomous flight, waypoint navigation, image capture, and image transfer, before moving on to modules that have been adjusted from last year, such as the autonomous payload drop, autonomous takeoff, and post-processing, which involves a brand new image processing algorithm. Specific components such as the UGV drop mechanism and parachute were tested thoroughly before integrating it into the plane. Other subsystems such as image processing were able to achieve simulated in the lab testing to test their algorithms for classification accuracy. Bench level testing such as this allowed our team to be better prepared for full mission flight tests as well as minimize risks. Each full mission test was designed over the Kawainui Model RC plane field in Kailua on Oahu, Hawaii. These tests consisted of all the tasks to be attempted at the competition in the following order: autonomous takeoff, waypoint navigation and obstacle avoidance, autonomous payload drop, search area task, and autonomous landing. The team simulated mission flights based on the size and range between waypoints given in the previous years. Of course, many issues were encountered during the testing period. Some of these issues included bad cable connections, incorrect center of gravity, or abnormally slow takeoff and cruising speeds, all of which provided our team the opportunity to learn and grow by correcting these issues. So far, UHDT has had a total of 20 flights, 7 of which were full mission flights. However, due to the inaccessibility of an airfield suitable for autonomous landing, only 3 flights were done with a fully autonomous mission. 12 flights were done in autonomy with manual landing, and 5 flights were done all in manual. The average time in autonomy is about 8 minutes, and the average time in manual is about 7 minutes. Autonomous flight will be achieved with a hand launch and autonomous climb out. According to the Mission Planner software, the waypoint capture will be within a 30-foot radius based on GPS locations. In order to deliver the UGV gently and safely to the ground within a 75-foot radius of the target, a 36-inch annular parachute is used. This specific parachute features a drag coefficient of 2.2 and it was tested to be able to drop the 2.5 payload to the ground with a max descent velocity of 11.81 feet per second. The parachute would be loosely wrapped with the suspension lines beneath to allow for more instantaneous opening and slower descent. A mathematical model was created to determine the drop location to the best of our ability. However, due to the unpredictable nature of the wind, it proved to be very difficult. resulting in drop locations with a large error in both distance and direction. On the day of testing, an average wind speed would be taken before flight and it would be inputted into the mathematical model. The model would then give us a distance, and the payload release location would be set to that distance according to the target location reference. To best mitigate drift in sidewards directions, the UAS would drop the payload in headwind. However, as the wind is very sporadic and chaotic on Oahu, the wind direction would often shift and cause the UGV to drift in a completely different direction than expected. We experienced this several times during flight tests in which the wind would cause the UGV to drift in different locations each drop. So we experimented with the way we wrap the parachute on a few drop tests and noticed that a delayed opening caused a drop location that is more true to the release location. So instead of releasing the payload according to the distance given by the mathematical model, it may be more beneficial to release the payload directly above the drop target. This delayed opening reduces the amount of drift with the offset of causing a larger snatch force, which is basically when the parachute fully inflates. And so, out of the 7 successful drops that we've had, the payload has landed within 75 feet of the target 3 times. 3 of the successful drops were done with a delayed opening, each of which has landed within 75 feet of the release location. More testing up to the competition date will be done to confirm this. However, at this point, we are more confident in the results of the delayed opening and are 80% positive that the UGV will land within 75 feet of the target location. Obstacle avoidance was tested by creating no-fly zones on Mission Planner in order to simulate the areas in which the UAS needed to avoid. Additionally, the mission was designed over an RC plane field at which many areas needed to be avoided due to safety, inaccessibility, and/or state or federal regulation. These were added into the consideration for obstacle avoidance. UHDT predicts 100% accuracy for obstacle avoidance during the waypoint navigation and air delivery portions of the mission demonstration. However, the team will not be attempting obstacle avoidance during the search area task due to the nature of the bottom-facing camera. Autonomous landing will be achieved using a LiDAR module and various Mission Planner parameters and has been successful every time it was tested. In our conducted tests, we have been able to successfully run image capture and transfer. Images are captured by a Nikon Coolpix A camera, which is mounted to the bottom of the UAV. This camera has a 28mm focal length and a 16 megapixel effective resolution. The image's dimensions are 4928 by 3264 pixels with an average horizontal field of view of 40 feet. These images are then transferred autonomously through Wi-Fi and SFTP from the UAV to the image processing laptop and provide an acceptable image quality. After images are captured and transferred, UHDT utilizes an autonomous application program interface called API that integrates object detection, shape recognition, alphanumeric recognition, and color recognition. The first step of this process is OpenCV blob detection and shape recognition. Blob detection identifies groups of pixels within an image. These are groups of pixels with similar grayscale values, and shape recognition detects edges to determine the shape of the target. The shotgun approach of blob detection has outputted several false positives in previous years, so objects are filtered through k-means color recognition. Nearly all of these past false positives have been filtered out by the filter of the color recognition algorithm. 83% of our tested color combinations were identified correctly. Finally, alphanumeric recognition is done by a convolutional neural network, which identifies alphanumerics by comparing against the millions of images used to train against the model with the CNN. 80% of alphanumerics have been identified correctly from tests. In total, these 3 post-processing steps have taken up to 3 to 5 minutes to run on 50 images. After post-processing, targets are localized through the built-in georeferencing function on Mission Planner. This function requires the time offset between the ground station and the camera that captured the original images. From multiple tests and the hundreds of target images, localization has had an error between 75 and 125 feet, and so we are expecting between 16% and 50% of this category. Throughout this past school year, the UHDT team has collectively done about 100 hours of testing. We have seen our work on the UAS fly in the sky and plummet to the ground, but we did not let this deter us from our mission. Each time the plane went down, we picked it back up, dusted the dirt off, fixed what needed to be fixed, and brought it back into the sky. Any challenge or obstacle that was placed along our path was overcome by the hard work on our team. Each failure was an opportunity to learn, and we learned a lot. Through our errors came growth, insight, and experience to which we applied to the following tests. Due to some of the catastrophic crashes we faced, we weren't able to get the amount of testing that we originally wanted, but what we have gotten so far is enough for us to be confident in the scores we believe we can achieve. Overall, if we take all the testing that we have done over the past year, UHDT has a potential mission demonstration score of 53.74% out of 60.